One of the problems we have with the way we solve equations that have constant coefficients is that the methods don't always extend to equations with non-constant coefficients. So if I want to deal with something and the coefficients of my derivatives are not numbers, right now, I'm screwed. There is a general method for doing this, but a particular special case exists in the form of Cauchy-Euler equations. Now, Cauchy-Euler equations are rigged. They are rigged so that the coefficient for each derivative is a polynomial, a monomial of degree the same order as the derivative. So if I have an nth derivative piece, I have a number and then a power of x to the n. And for each of these, the same thing occurs. Every one of those, the coefficient is exactly a number, a power of x, and the power of x has to match with the order of the derivative. And the AI is a constant. So let's just start with the easiest non-trivial case. Let's look at a second degree version of the second order. A2 x squared y double prime plus A1 x y prime plus A0 y equals g of x. If this is the right-hand side is not zero, then I'm going to use variation of parameters. So I'm going to start with the idea that we're working with zero. And find our complementary homogeneous equation. And if I can find that, then I can use variation of parameter to find the part for g of x. Okay, wait a second. There's a distinct advantage that Cauchy and Euler noticed here. Y double prime, but I have an extra x squared. Y prime, but I have an extra x. So if I had a power of x going on here, what happens when you take the derivative of any power of x? X to the whatever. It's derivative of that. Power rule. I get one lower power, right? Which means the y prime is going to have one fewer x's, but there's an x next to it. Y double prime is going to have two fewer x's. There's an x squared next to it. So this actually works out to be something nice if a solution is of the form y equals x to some power. Then by the power rule, now what happens when you take that and you put that back in? Well, this x squared here is going to make this x to the m. This extra x here is going to make this x to the m. And this one is already x to the m. Which means this works if my coefficients work out right. If I factor out x to the m, I get a bunch of numbers. And that's a quadratic equation. Yes.
Whatever the x next to a. Oh,
I multiply those together, I get x to the n, factor outside. The same thing that happened to the x squared next to a2. It came out with all of the other x's. This is a quadratic in the variable m, which means you can find the m's that make this work. Just like we found the r that made it work for the other versions. Same idea. The problem is, unfortunately, it is not as simple as just reading out the numbers and putting the m squared, all of that, because in this first factor, I have m times m minus 1. So I really need to remember to put that in here. The no coefficient here is a 1. So it's 1m minus 1 minus 3m minus 2 equals 0. That's my quadratic, which is not just m squared minus 3m minus 2. Because when I multiply this through, I'm going to get 1 extra m. So my quadratic is actually a little different than just a string of coefficients. But I'm in the same boat I was a week ago. I have a quadratic equation. Solve it. I'm the guy who freely admits to being a sick freak. I'm going to complete the square. You could rip out the quadratic formula just as well. But there are your roots. 2 plus or minus the square root of 6. But those are the values of m. Where did m come from? The very beginning of this discussion.
why?
X to the power m, which means I know what the answer to this corresponding homogeneous equation is. YC is C1 x to the 2 plus root 6 plus C2 x to the 2 minus root 6. X to the M1, x to the M2. Those are my roots. Those become my powers. If you had initial conditions or boundary conditions, you could solve for C1 and C2. Just like you did on the homework you just gave me. If we had a non-homogeneous term on the right side, which we didn't in this case, it was equal to 0, I'd use variation of parameters. My big Wronskian and my ugliness, I do the same thing. We know how to do it. I don't like it, but I know how to do it. Questions? If I were to follow through the variation of parameter idea, I would have to divide by the leading coefficient next to the y double prime to get y double prime all alone, because I need the p of x and the q of x thing. So I would be dividing by x squared, which means I can't use x equals 0, yes? 2 minus square root of 6. It's the value of 2 minus square root of 6, roughly.
Almost negative.
Negative. It's negative, which means this is really a 1 over x, which means the domain of this function doesn't include 0 in the first place, does it? I'm all the way back to chapter 1. Every differential equation has an interval where it works. This is either defined for x less than 0 or x bigger than 0, but the interval can't include 0 because I've got a 1 over x term here. All right. This is going to occur on any auxiliary equation where I have two distinct real roots. E to the R1, e to the R2, same idea. So what happens? If I only have one root, one m, I just got one value. Wait a minute, back up. I have one solution. How do I find the other one? I solve the auxiliary equation. I got one root. It's repeated. What do I do now? You just gave me a bunch of these.
When it's repeated, like when it's like e to the x, x e to the x, and x 2m or x squared.
Well, if I add another x, that would make it x to the m plus 1, right? But we added another x in the equation here. How did I get that extra x with the e to the stuff?
How do you get it?
How did I get the extra x?
So it's like R minus one.
times r minus 1. I got 1 twice, so I said, oh, well, we're always going to get an extra x. But we always got the extra x because we did something to show we always got the extra x.
Then the y1 plus integral.
Y2 equals y1 integral e to the negative integral p of x dx over y1 squared. That was our reduction of order formula. That's where the extra x came from every time, Noah. I just didn't pull it out of thin air. I did this once and I showed that for every e version, this always results in just an extra x. But now I don't have the e, so what the hell's going to happen? Well, where do I get p of x from? Except before I get that, I have to divide by the first part. So the first thing I need to do is rewrite this y double prime plus. Well, then it's a1 over a2. Get this one tight. It's a1x over a2x squared. Cancel one of the x's. So this is p of x right here. It is next to the y prime, but it's only next to the y prime when the coefficient of y double prime is 1. So, means that goes up here. Integral of minus a2 over a1x dx. Well, a1 and a2 are numbers. Oop, I switched the two numbers around. Let's not do that. It's a1 on top and a2 on the bottom. Got to put the right number in the right place. Wait a minute. Just take the constant out front. What's the integral of 1 over x? Oh, that was nice and easy. So that is what goes up here. y1 was x to the m. Integral of e to the this negative a1 over a2 ln of x over y1 x to the m squared dx. What happens up here? Only when they're next to each other. So what do I do with the a1 and a2 stuff? Aha. So that's going to become a power on the x. X to the m integral x to the negative a1 over a2 over x to the 2m dx. Sheesh. Okay. I said m was the one solution to our auxiliary equation, right? M is just one root for the auxiliary equation. Hang on a second. The auxiliary equation, a2m m minus 1 plus a1m plus a0. That's my auxiliary equation, which is the same as a2m squared plus a1 minus a2m plus A0. This is a quadratic. We were setting it equal to 0. Okay, people. If a quadratic equation has one solution, what's the graph of that quadratic equation look like? Every quadratic equation looks like that. What's special about that parabola if it only has one root? Vertex is at. And what's the equation for the vertex of a parabola? Start the quadratic formula for me. But the plus or minus square root would give me two different things, right? The only way it gives me one thing is that the plus or minus is 0. So the top is just negative b over 2a. So that means that m is equal to negative b over 2a. Now, why am I giving you that piece of information? So that we can simplify this. Because up here, we have x raised to the a1 over a2 with a minus sign. And on the bottom here, we have x to the 2m. What happens when I put a 2 over here? Oh, it cancels out the 1 on the bottom here. And if I distribute the minus sign, I get that. With me so far? How does this simplify? What do you do with a root that's a power of x that's on the bottom? And do what? But before I can multiply it, what do I have to do to the power? Aha. Hey, wait a second. Minus a1 over a2. Minus a1 over a2. What happens? Almost. I get a negative 1. Wait. Where is this crap? This crap is inside an integral, isn't it? y2 is x to the m times the integral of this thing. What's the integral of x to the minus 1? Noah, in the exponential case, we always got an extra x. In this case, we get an extra ln. Every damn time. But that's only for Cauchy-Euler equations. That's only if the equation is rigged like this and we have a repeated root. Yay! I'm going to mess with y'all. Here's my example. What is the auxiliary equation? I don't have to have the format for the auxiliary equation memorized if I remember that I'm looking for something of x to a power. I can always go over here to the side and write y is x to some power, so y prime is mx to the m minus 1, and y double prime is m times m minus 1, x to the m minus 2. I can get the auxiliary equation back without having to try and recite it from memory. X squared m minus 1, x to the m minus 2, plus x, m to the x, m minus 1, plus 0 equals 0. And now I factor out all the x's because there's an x to the m everywhere. What is my auxiliary equation when all is said and done? So I want m squared to be equal to 0. What's my repeated root? It's m equals 0. So that means that I get y c is c1 x to the 0 plus c2 times what's my second solution? Only the 0 only goes on the x power. It doesn't go in the logarithm. There you go. Wait a minute, what's x to the 0? 1. So this is really c1 plus c2 ln of x. Sneaky mother. So again, if I have a quadratic auxiliary equation, I can solve for the right values. If it's repeated, I add another term, this extra logarithm rather than an extra x, because I was already working in x. Another way to think of it is that e to the ln gives me x, right? E and ln cancel each other out. I already had the x's, so I need to cancel it out. Let's try this one. You're grinning at me, Mia. Talk to me. Son of a... All right. All right, now you're just pissing me off. Really? What this means is that the correct answer is x to the 2I. Right. Sure it is. What the hell is x to the 2I? I know how to deal with e to complex. It's the x that's bothering me. Didn't I just say that e and ln cancel each other out? Let's take this x to the 2I. And we'll write it as e to the ln of x to the 2I. Wait a minute, I have a power of a power. What do I do when I have power of power? I multiply them together. So this becomes, and I'm going to write this power a little differently, e to the I 2 ln of x. I just put the I in front. Okay, let's go back to last week. E to the I theta. E to the I number, right? What did we do? R e to the I theta. What do I do with the e and the I? They became sine and cosine. I'm actually going to write this as cosine of 2 ln x and I sine 2 ln x. When it was just e to the number went inside here. Now it's e to the stuff. Wait a minute. I got an extra ln x floating around, right? Cody, just like with the repeated root, I get the extra ln x. Oh, I like that part. Instead of just being 2x, it's 2 ln of x. This is on par with what we just finished doing in the previous one. Now, it's this I that bothers me, right? That's ugly. I don't like it. But this is just the positive one. We can do the same crap we did back in section 4.3. And I say, oh, so really what I want to use is I want to use for YC, I want to use C1 cosine 2 ln x and C2 sine 2 ln x. And that works. Now, I will freely admit this problem was rigged and I got just plus or minus 2I. So what happens, I'm going to make something up. Suppose I got m equals -1 plus or minus 2I. Well, then I'd do the same thing. I'd go, oh, x to the -1 plus 2I is really x to the -1 and then x to the 2I. Because when you add powers, you multiply with the same base. But we just did x to the 2I right here, didn't we? So if I were to write out the solution for this bit, it would be y equals C1 x to the -1 cosine 2 ln x and C2 x to the -1 sine 2 ln x. In general, if my root is a complex number, the alpha part is going to go here, and the beta part is going to go here. I hate memorizing formulas. Every time I run into this problem, I do the conversion with the sine and the cosine the long way, but that's because I really, really, really like complex numbers. And if you don't, feel free to write this down on your formula sheet. Questions? Yes, ma'am.
The alpha sine or cosine be ln of x.
Yes.
Beta.
Beta, yeah. X to the alpha, cosine beta ln x. X to the alpha, sine beta ln x. Yeah. Every time. But rather than me go through the one with the general and do all the derivatives, okay, we'll do an example and then, hey, this is going to work all the time. By the way, it works for higher powers. I did second order. We can do third order, fourth order, fifth order, however many, as long as we can solve the stupid equation, we're good. Every time a root repeats, we get an extra factor of ln. And that means it is possible to get ln squared out of this problem. Every time I have a repeated complex thing, I'll get an x cosine and an x sine, and then I'll get an ln on those if the complex part is repeated. If I give you an initial value or boundary value, you can solve for C1 and C2. This is not homogeneous anymore. Same process requires as required last time. Solve the homogeneous first, and then we'll solve the non-homogeneous part. So I'll start by solving the corresponding homogeneous equation. So do that first. By the way, we've been using ln of x. If I really want to be anal retentive about it, I should be using ln of the absolute value of x. But since this function is undefined at 0, our interval is either all bigger than 0 or all negative 0, I really only need to involve that absolute value if my initial condition involves an x value that's less than 0. My corresponding auxiliary equation becomes m squared minus 2m plus 1 equals 0. So m is 1, repeated. With that in mind, what is the corresponding homogeneous solution? YC. The complementary solution. Perfect. But that's just for the homogeneous part. And this is a non-homogeneous equation that I want to solve. In order to solve that, I need to use variation of parameters. I need to do those determinants and do the Wronskian and all that fun jazz. So in order to solve this, I first need to rewrite the original equation with y double prime alone. I'm sorry, not this one. This one. The one that starts the non-homogeneous part. Because this is f of x. So now I'm going to do 3 determinants. I'm going to do the Wronskian of the 2 solutions. W, y1, y2 starts with x and x ln of x. What's the derivative of x? Good. Derivative of x ln of x is ln of x, derivative of x is 1, and then plus x times the derivative of ln, that's x times 1 over x, so that's 1. So when I do this Wronskian, I get x ln of x plus x minus x ln of x. I just get x. That was nice. Now, W1 replaces the first column with 0 and f of x. And I do my determinant. And I get
2, maybe 2.
because the other piece is 0. W2 replaces the second column. That determinant is, yay. So U1 prime is negative 2 ln of x. Negative 2 ln of x over x. And U2 prime is 2 over x, because it's W1 over W and W2 over W. And now I can integrate. U1 is the integral of negative 2 ln of x times 1 over x dx. Instead of writing as a fraction, I just wrote them out one after the other. Because then, this is a u sub. U equals ln of x, du is 1 over x dx, so I get minus u squared, or minus ln of x, all squared. I don't need a plus c. U2 is the integral of 2 over x dx, which is just 2 ln of x. And then the particular solution, yp, is u1 y1 plus u2 y2. Y1 was just an x. And u2 is 2 log x. What was y2? Y2 is part of my solution. Y1, Y2. That's back from here. U2 is 2 log x times Y2, which is x ln x. Hey, wait a minute. This is going to be x log x squared, isn't it? So I've got 2 of them, and then I subtract 1. I get x ln of x squared. Ta-da! We found not just our corresponding homogeneous solution, we also found our particular solution. If I had initial conditions, I could nail down C1 and C2. When I first saw this method, I was stunned at the idea that the way in which we solve these equations is so close. When the coefficients are constants and when the coefficients are rigged to be powers of x. Well, it turns out you can actually turn a Cauchy-Euler equation into an equation with constant coefficients by doing a substitution. If you sub x equals e to the t, then this entire problem becomes a problem in t with constant coefficients. Page 170 to 171 walks me through that process. But now that I have the method, I really don't care about doing that substitution. That's just the way this method came to be. Was a transformation of the variables allowed me to make my life simpler. Remember that phrase. Because in another week, a transformation of variables making my life simpler is going to be the way I generalize this. But that's in a week. Between now and then, we have some other stuff to do. So I will see you all on Friday. Have a wonderful rest of your day. And now, Mia, you can go take a nap.